Hi, I'm Emily and I'm a sociologist and I teach statistics. So in this video, we're going to go over key terms, all of the basics you need to know to succeed in this statistics course. But if you think you're an old pro, there's definitely stuff that's in here that's worth watching for you too. So we're going to build on the basics and I can't wait to teach you. As a quick reminder, on this channel, we talk about how math is for everyone, and I truly mean it. So forget what you think you know about your own math abilities. With the right strategy and mindset, learning statistics can and should be fun. And also for folks who think that they have a pretty solid foundation with the basics of statistics, I encourage you to watch through this video and hang on tight because I'm going to make sure to build upon the basics as we go through. So let's get started. Definitions and key terms, setting you up for success in a statistics course. What is statistics anyway? Well, statistics is formally considered the collection, analysis, interpretation, and presentation of data. Yes, it's a form of mathematics. We're going to talk about two forms of statistics in this course, descriptive statistics and inferential statistics. Now that might sound fancy, but let's break it down. Descriptive, the hint is in the word itself. We're going to describe and summarize our data. We're not making any predictions. We're not making any inferences about future events. We're just saying, what are the basic descriptions of information in our data set already? So for example, what is the height of the average person in our sample? We're not making any predictions about people outside of our data set or about new members of our data set. We're just describing the information that already exists. Let's talk about inferential statistics. Again, the hint is in the beginning of the word, inferential, inference. We're making inferences using this form of statistics. Inferential statistics allows you to draw conclusions from the data. One example that might resonate is the probability of winning a game of blackjack, or 21, based on the cards you've already drawn. So you're analyzing the information you already have in your data set, which are the cards in your hand, and you're figuring out what the probability is that you'll be able to pull the cards that you need. So you're making inferences about the data. Let's talk briefly about probability. Probability is a mathematical tool that's used to study randomness. Yes, our universe is built upon chaos, and there's a lot of randomness that we need to analyze and make sense of. So probability deals with the chance or the likelihood of an event occurring. I really like this video. I'm going to put a link to the video in the description. I really like how he breaks down this entire concept of mapping out on a number line all of these words that we use to describe probability. So I would definitely encourage you to check out the video. I'm going to do some summary on the next slide. When we talk about probability in our casual everyday lives, we often misuse pretty technical terms that have mathematical meaning. So let's make sure that we get on the same page with how to use words that describe the probability of events happening. I created this fun little table, and we're going to go through and talk about each row in the table and what exactly it means. So let's go row by row. In our header row, you can see we're going to be comparing equivalent language in words, as a fraction, as a decimal, and as a percent. So all of the terms that are shown here have equivalent meaning. So if I say that something is impossible, could it ever happen? No, it'll happen 0 times ever, or 0 shown as a decimal, or it will happen 0% of the time, right? So even if something were only possible 1% of the time, that doesn't mean it's impossible. It has to truly be impossible, never likely to happen. Now let's go down the next row. If something is unlikely, that means that it could happen, but chances are it's not going to happen. So if we wrote this as a fraction, it would mean that our probability would lie somewhere between 0 and 1/2. Or if I wrote it as a decimal, it would lie somewhere between 0 and 0.5. Or if I wrote it as a percent, the probability that this would happen would be between 0% of the time and 50% of the time. Now, it wouldn't be 50% because that would mean that it's as likely to happen as not happen. We represent that probability as a fraction as 1/2. Or if you were asked to write it as a decimal, we write that probability as 0.5. Or, again, as a percentage, it happens 50% of the time. Again, this truly means that 50% of the time it will happen and 50% it won't. There can be no difference because it has to be as likely as not likely to happen. Now let's keep going with our pattern. Let's talk about likely. If something's likely to happen, it is not certain it will happen, but it's definitely going to happen more than 50% of the time. So we represent that as a fraction as between 1/2 and 1. Or as a decimal, we represent that as 0.5 is less than x, our probability, which is less than 1.0. Or as a percent, we would say that our probability x is greater than 50%, not greater than or equal to, but greater than 50%, but it's also less than, and not less than or equal to, but it's less than 100%. And then obviously, if something is certain, we would represent it as a fraction of 1, a decimal of 1.0, or as a percent, as in this will happen 100% of the time. So if I ask you, is it going to rain tomorrow? And you say, I'm absolutely certain it's going to rain tomorrow. Do you truly mean you're 100% sure? Right? We use these terms more casually in our everyday language, but I challenge you in this statistics course to use them as precisely as possible. Now let's talk about some other key definitions you need to know for this course. Parameters and statistics are two kinds of information that you're going to be working with throughout this course. Now, parameters are a number that describe the population. The population is the entire group of people that you want to know information about. So, for example, what if I wanted to know the average number of points earned by math students in all math classes? That's a pretty big population. Usually what we do as statisticians is we take a random selection of this entire group of people. We can't always interview or get the data on every single person. So we take a random sample and then we work with a small group of people to figure out a statistic. A statistic is the number that represents the property of the sample. For example, once I take a random selection of a really big group and I have a smaller group to work with, I can ask all of these students, what was the average number of points that you earned? So maybe this person earned 5, this person earned 6, this person earned 4, right? I'm asking just a few people their specific information. That specific information that I'm working with for my sample is called a statistic. What we then do is use that statistic to make an inference, right? Inferential statistics. We use that statistic to make an inference about what the population mean is, right? So you're going to hear this a lot later, but this is mu, the population mean. That's the parameter of the population. So if I want to know about an entire population, I'll take a random selection or a sample, and I'll work with that sample to figure out the statistic about that sample. Then I'll use that statistic to make an inference about what's happening in that big population. And again, why would we want to do this? Well, we're trying to save time, we're trying to conserve resources, and it's not always possible to get data on the entire population. So sampling is a really key tool that we use in statistics. So again, big takeaway, understanding the difference between parameters and statistics. if our sample can tell us about a population, should the statistic be different from the parameter? You'll notice that sometimes we have differences between our statistics, right? That's the information about our samples, and what is true about the parameters of our population. However, if our sample is representative, then this difference will be minimal. A representative sample is a sample that accurately represents the population under study. The sample must contain the characteristics of the population in order to be representative. So this move between the population all the way over to sampling is a really critical one for making statistics that have meaning. All right, let's talk about a few other terms that are going to be important in this course: variables and data. So a variable is a characteristic or a measurement that can be determined for each member of a population. Variables can be numerical or categorical. Now, if you're looking at a table like this, even if you don't know anything about the data set, one key tip is that column headers in a spreadsheet tend to represent variables. In this course, you can assume that this top row has all of the variable information in it. So here I can see that this table has variables of a position, and see, this makes sense: accountant, CEO, these are all different position types, right? And then salary is another variable, because you can see there's individual instances of salary values as you go down. Office, well, here it looks like office location is a variable, because you can see different cities where the offices are located. And I'm going to guess that this one is a phone extension number. And you can see these are different phone numbers where employees might be reached. So now that you understand these are variables, now we can talk about data. Data are the actual values of the variable, and they can be numbers or they can be words. So for example, this right here, integration specialist, is a data point. Or here, London, is a data point. One last thing to mention: statisticians often call rows of a data set observations. So this entire row here is one observation. And typically it represents maybe one person in a data set, at least in the sociology context. So here you can see one person is a CEO. The salary is $12 million. Must be nice. The office is in London, and the extension is 5797. So this entire row of data organizes one observation about one person. Let's talk about two other terms that you may be familiar with: mean and proportion. Mean is often called the average. There are different ways to take averages, but we commonly are talking about the mean when we talk about averages. This is a fancy word. It's a measure of central tendency. All that means is that this is where all the values are added together and divided by the number of values in the sample or population. So when you take the average, it's kind of like when you go to dinner with your friends and you divide the total bill by the number of people there. Not everybody spent the exact same amount of money, but it's a really quick way to get the average amount that somebody spent. A proportion is a number considered in a relation to a whole. So, for example, the proportion of men in a kickboxing class. These concepts will be revisited in later sections of the course. Now let's talk about types of data. Before I go on, take a moment to think about this. Do you already know the difference between quantitative and qualitative data? Take a look at this cartoon for a few seconds as a refresher. Let's get into the definitions. Qualitative data are the result of categorizing or describing attributes of a population. Qualitative data might include examples like hair color, blood type, racial ethnic group, the car a person drives. These are categories that describe people, and it's really hard to think of them in terms of numbers or values, right? But quantitative data are always numbers. Quantitative data are the result of counting or measuring attributes of a population. So let's think of examples. The amount of money, a pulse rate, weight, number of people living in your town, or number of students who take statistics. These are all values that we can think of as numbers. Now again, think about what you already know about data. Can you parse quantitative data into discrete data and continuous data? Even if you're not sure what that means, take a moment to look. What do you notice as different between these two groups? Quantitative data may be either discrete or continuous. All data that are the result of counting are called quantitative discrete data. These data only take on certain numerical values, so I circled counting, and here's why. If you count, you only say whole numbers, right? 0, 1, 2, or 3. So for example, if you count the number of phone calls you receive each day of the week, you might get these kinds of whole number values. That is quantitative discrete data. We can't have a data point such as, I got 2.5 calls yesterday. All data that the result of measuring are quantitative continuous data, and we assume that we can measure this accurately. So again, here I'm not talking about counting, I'm talking about measuring. So think about measuring somebody's height. You can measure in centimeters, you can measure in fractions of centimeters, you can measure even in whole feet if you like, but you could get very precise, down to the very smallest decimal of someone's height. The variable is continuous. It continues in a decimal form beyond the discrete forms of whole numbers. As a last tidbit for today, let's talk about frequency tables, and levels of measurement. I'm going to tell you now that some statisticians quibble about differences between these variables, but my point is to help you understand these levels of measurement so that you can apply them in your own introductory statistics work. Nominal variables or nominal scale data are not ordered and they don't have an inherent numerical value. Think of nominal data as categories, categorical data, or labels. So here are some examples. Just categories, colors, names, labels, favorite foods, yes or no responses, or even numbers that aren't quantitative in meaning. This is a little tricky, but think about a phone number. Can you add, subtract, or divide a phone number or an ID number like a social security number? Not really. That kind of number is just a label. So we consider that a nominal variable. Ordinal scale data can be ordered, but it's tricky to exactly quantify or turn into an exact value. So here are some examples. Socioeconomic status, like low income, middle income, and high income, those definitely have orders, but it would be very hard for all of us to agree on exactly what the definition is for low income versus middle income, unless you had some kind of rubric. Or think about this, education level. Highest education earned being high school, a bachelor's, a master's, or a PhD. These are definitely ordered, right? We know that a PhD is more education than, say, high school. But everybody takes a different amount of time to complete their degree. And it's hard to quantify the differences between these degrees. So instead we just say that they're ranked in an order. Now, interval variables, these data have a definitive order, but the difference between the rankings is consistent. However, there's no true zero that has meaning. So look at some examples here. Think about temperature, like degrees in Fahrenheit. If I told you that it was 40 degrees in the morning, 45 degrees at noon, and 50 degrees at sunset, you would be able to know that it went up 5 equal degrees each time in an interval. Temperature in Celsius is also formulated that way. There's an interval and is applied evenly each time. pH or SAT scores or credit scores, again, they all have intervals that make sense. However, you can't get an SAT score of 0. It doesn't have any meaning. Or a credit score of 0. That wouldn't mean you don't have a credit score. Also, think about these temperatures. If it was 0 degrees Fahrenheit or 0 degrees Celsius, it wouldn't mean that there was no temperature at all. It would just mean that on the scale, you would have reached 0 degrees. Now here's my nerd note. Some statisticians consider Likert scales, like rate your happiness on a scale from 1 to 5, to be interval data. And some consider them to be ordinal data, in part because respondents might not have a measurable, statistically meaningful interval that they consider when answering such Likert questions. For the purposes of an introductory statistics course, students should make the argument either way, and it's okay as long as you explain clearly. For the purposes of more advanced statistics, this is a distinction that's necessary for considering what complex statistical models are appropriate to use with which variable type. Let's talk about the final, 4th level of measurement, ratio variables. These data have a definitive order, and the difference between rankings is consistent on a scale, just like interval variables. But in addition, it also has a clear definition of what 0 or even 0.0 means. When the variable equals exactly 0, it means that there is none of that variable. So let's start with some of these examples here. Enzyme activity, if you had a score of 0, it would mean you had no enzyme activity. Or dose amount. If you were told to take 0 pills, that would mean you take no pills. Also, think about temperature measured in Kelvin, which we don't really use often except in the sciences. But if you had a temperature of 0.0 Kelvin, that really means that you're at absolute 0. There is no heat. So when you're thinking about the differences between interval and ratio variables, ask yourself, is the value of 0 really mean there's none or nothing, or isn't any of that thing? Think about number of kids. Is that a ratio variable? Yes, because when you have 0 kids, that means you do not have any. I encourage you to take a screenshot of this handy dandy chart. I think it's really useful for when you're going through tricky variables and trying to figure out what level of measurement it uses. So you can follow through this flow chart to see if your categorical or metric variable is nominal, ordinal, interval, or ratio. And here are some more good examples. Now let's talk about frequencies. How much or how often does something occur? Get your freak on. So let's talk about definitions. A frequency is the number of time a value of the data occurs. A relative frequency is the ratio, like a fraction or a proportion, of the number of times the value of data occurs in the set of all outcomes to the total number of outcomes. So, really simply, if you want to find relative frequency, divide each frequency by the total number in the sample. We'll go through examples in another video. Also, I want to introduce you to the term cumulative relative frequency. This is the accumulation of previous relative frequencies. To find the cumulative relative frequency, add all the previous relative frequencies to the relative frequency for the current row. Again, these are definitions I'm introducing now, and we'll go over in further detail in other examples. But for now, let's talk about how to display frequencies. There are a few different options that are appropriate in different circumstances. Let's look at option 1, a frequency table. Now, The X values here represent all of the possible scores, so it looks like it's possible in this data to have had a 1, a 2, a 3, a 4, a 5, or a 6. To help it make more sense, let's pretend that we took a random sample and we asked members of this random sample how many pets they have. So as you can see here, this is the frequency of people that had these possible scores. So one person had 1 pet. 2 people had 2 pets. 2 people had 4 pets. And 1 person had 6 pets. Probably fish in a fish tank. Again, F represents the number of individuals earning each score in your data set. Frequency tables allow us to easily see which score was the most common among individuals and to calculate proportions. So take a look here. What was the most common number of pets to have? To answer that question, we look at the frequency column. What was the highest frequency or the most people in a certain category? 4. It looks like 4 people had 3 pets. So we can say having 3 pets was the most common score in our data set. Now let's talk about displaying frequencies. One option is a histogram. A histogram is like shown on the left. They're used for interval or ratio data. What were those again? Exactly, they're ordered variables in which the scale is consistent between each value. Unlike bar graphs, however, there's no space between the bars. So you can see that all the bars are squished together. And the bar height indicates frequency. Another way to display frequencies is on a bar chart. But isn't that the same as a histogram? No. Remember that bar graphs are used for nominal and ordinal variables. Those are categories in which the scale isn't consistent. So unlike the histogram, there is space between the bars. Here, the bar height also indicates frequency. So it looks like if I'm looking at separate personality types, if I want to know how many people had a particular type, I just go up the y-axis to see what the value is. So it looks like here, 10 people had personality type A, 5 people had personality type B, and 20 people had personality type C. In each of these videos, I like to highlight my top 3 takeaways. Of course, it's not comprehensive, but it's just a review to make sure we're all on the same page. So, number 1, this video reviewed key probability and statistical terms, definitely worth reviewing before your first exam. We also talked about kinds of variables, qualitative and quantitative, and we reviewed the 4 levels of measurement, nominal, ordinal, interval, and ratio. Those would be really great to review too. And third, we had a quick introduction to just the definitions of frequency tables. We talked about frequency, cumulative frequency, and relative frequency, as well as histograms and bar charts. We're going to talk about those more, but it would be really good to review those definitions before you move on. All right, thank you so much for paying attention, and I'll catch you in the next video.